Hey everyone, welcome to the first video of BIOEN 335, and we're back for another quarter here with the homework videos to just help you get them set up and here to walk through some of the concepts with you all. And thank you for having me as your TA again. I really am glad that all of you all learned so much last quarter, and we're going to learn just a lot more this quarter as well, a continuation from last quarter. And again, I'll be here to support you all. If any of these concepts are confusing, please send me an email or come to my office hours. I will hold drop-in office hours today. I know it's not my normal schedule, but I know that the homework is due very soon, so I'm more than happy to help. Great, so without further ado, let's get started with homework 1, question 1. And this is a question that's very similar to what we saw in quiz section. So if we look, we have a tube. First, let's note the geometry. We have a tube. It's 10 centimeters long, and we have an internal diameter, right? Let's also note diameter of 6 millimeters. The silicone, which is basically the outer shell, right, has a density. We have the density right here, and we have a thermal conductivity K, and that's 0.2 watts per meters in Kelvin. And we have the internal temperature maintained constant at 10 degrees Celsius above the external temperature. So not 10 degrees Celsius, but it's above the external temperature. Then we're also going to ignore any thermal losses at the ends of the tube. So that is great. So always the first step that I recommend is drawing a diagram. So let's draw a diagram. We have our tube, sorry. Great, and now with our tube, we have essentially some thickness. So that means there's a layer. So this is, if you recall, very similar to our quiz section problem. So I know my drawing isn't the best, but that gets the general gist of it, right? So we have a length of 10 centimeters, and we know that the diameter is 6 millimeters. So we're just going to right away say it's 3 millimeters internal radius, right? Then we're also given rho 1.1 grams over centimeter cubed, and then we also have thermal conductivity K, 0.2 watts over meters Kelvin. And we're also given the temperature, the internal temperature, and please keep in mind, this is not like temperature initial and then temperature, like this is initial. I know that's confusing, but it means in and out, okay? It means in and out. The internal or inside and then the outside temperature, right? And we know this is 10 degrees above the external temperature, right? Out. And we don't know the external temperature actually. So we know that a change in 10 degrees Celsius is a change in 10 degrees Kelvin. And we should recall that from previous science classes. And now let's take a look. The T in, the inside temperature, is inside this, it's constant here. Okay, it's constant, and this is the outside temperature. So again, we have heat flux, right? Because this is higher, we have heat flux going from in to out, right? Through this thickness. And that's what we're looking at. I know last quarter we were looking at fluid flow through the tube, but now we're talking about heat, and heat goes this way. It goes from high to low. So let's keep going. So we have 2 cases for question 1, and this is the easy question. Don't get too scared by that. It's just to note how much time it will take. Pretty much all questions are doable for sure. So let's get started. A, we have the total heat loss, big Q, through the tube wall for the case where the wall thickness is 1 millimeters. and then where the wall thickness is 4 millimeters. So we have two different cases. Our first case, case number 1, is our thickness is 1 millimeters, right? 1 millimeter. And we have our second case where our thickness is 4 millimeters. So this should be pretty straightforward. We know that the inside radius, right, is at 3, right? And that's the same. It does not change. And what we're actually doing is we're adjusting the thickness, which means the outside radius. So this is the outside, right? Outside radius changes. So in this case, it's 3 plus 1, 4 millimeters, right? And in this case, it's 3 plus 4, is 7 millimeters, right? So I hope this makes sense. So we have two different cases, and what we're going to do is we're going to compare Q. So that means we need to find Q. So what relation will we need to use? Well, let's recall from our quiz section, we learned Fourier's law of heat conduction. Fourier's law of heat conduction. Right? And what this is, we have two relations. Our first relation is little q, right? Heat flux is equal to big Q, heat flow, divided by the cross-sectional area. And this makes sense because we said flux is through that unit area, right? And this is the cross-sectional area flow. And let's remember, when we talked about the tube, right, flow, the circle was our cross-sectional area, right? But now, if we ignore the sides, right, as the problem stated, our cross-sectional area is actually through this entire surface area minus the ends of the tube. So it's essential that we're really thinking about where are we having flow and what kind of flow, right? So that's our first relation. And the second relation we talked about was with the thermal conductivity constant. And we described how that's different for each material. That's really similar. An analogy to that is, as we said, the viscosity of a fluid, right? And that viscosity of a fluid changed based on which fluid we were flowing through. So in that same way, let's write that out. So we have Q again is equal to the negative K dt over dr in this case, radius, right? We're in cylindrical coordinates. If this was rectangular coordinates, it would be dt over dx, right? So it's important that we're keeping that in mind. And essentially, what do we need? Well, looking back at the question, we need Q, right? And it looks like we have K, we have T, we have cross-sectional area. So it makes sense that we're going to use that relation. So we need to find Q. So we actually, if we think about it, we need to find Q as a function of dt dr. And why is that? Well, that's because, well, K is constant, AC is constant. Actually, that slightly changes, right? That slightly changes as well, because as we have bigger thickness, we have bigger radius. And the dt over dr, that's actually because the temperature change, right? T in to T out, no matter what, it's going to be the same. But we're also talking about over what distance, right? So the temperature profile does change, right? It's over a different distance. So let's actually figure out what that means, right? That means we need to look at this and say, well, we're going to put Q AC is equal to negative K dt over dr. And that means you can say, so I'll move right in the middle here. Q is equal to negative K times the cross-sectional area times dt over dr. Great. And we know our cross-sectional area is what? Well, we know first 2 pi r, so circumference times the length is that surface area. Surface area. So remember, the surface area is the cross-sectional area of flow. All right, this is surface area. Great. Well, let's keep going. Let's put that in to our expression. So we have Q equals negative K 2 pi RL times dt over dr. And exactly what we did in class, we're going to move the dr over and the r over. Let's use a different color to the other side. So we have Q over R dr. The Q can be on either side, you know, and we have equals negative K 2 pi L times dt. And we also have the integral here too, right? And we need to remember it goes from the internal inside radius to outside radius, and the temperature goes from the inside temperature to the outside temperature. So let's remember to put these in here, all right? It's important. It's important because now when we solve for it, right, we have Q times the natural log of R outside over R inside, right? And that's equal to negative, I'll just write it out a little nicer, 2 pi KL times, and then if we were, right, if we derive it, it's T, and then we would plug it in, right, T0 Ti, right? So that would be T outside minus T inside, right? And we have the negative here. This is why it's important. So when we have the negative and we want to move this over here too, we essentially have our final expression. Q is equal to 2 pi KL times T in minus T out because of the negative. And that's going to be over the natural log of, oh, I made a mistake. R in R0 over, or RO out over R in. And essentially, this is our expression for Q in terms of that radius, right? We have the outside radius. This changes. This changes. And what stays the same? All of this stays the same. Stays the same. It stays the same. It's a constant in this case. Sometimes it might not be a constant, but in this case, it's the constant. And one thing to keep in mind is this is the general form for Q with a cylinder with assumption. What's that assumption? The assumption is that the ends of the cylinder don't conduct heat, right? They're negligible. That's the only way that we got this expression, right? And if it wasn't the case, then we would actually add the two areas of that circle because that would also be considered cross-sectional area. But in this case, we don't. So that's the assumption that we're making that gives us this formula, okay? All right, so, you know, I like to make things a little simpler. So let's make things simple. So we have our constant. Well, what is that constant? Well, we have 2 pi K L T in minus T out, right? And that essentially just becomes 2 pi 0.2, if I recall, is 0.2 watts over meters Kelvin. And notice how I'm putting in units here, right? The reason I'm putting in units here is because we need to make sure that we are plugging in everything the right way. Already we have centimeters and we have meters here, right? So we can convert this to 0.1 meters. And that should allow us to start canceling out, right? That doesn't count anymore. And essentially, we have a constant of 0.4 pi watts. And that's on the top, right? That's this right here, this expression right here. So that means we can even further simplify this question to say 0.4 pi watts, right, over natural log. And we have the outside radius over the inside radius. How nice is that? And our total or our final answer is in watts because this is dimensionless, right? Because it's dimensionless, right? First you have it canceling and then you also have the natural log. That means we have our correct expression. Now, what's the final thing that you need to do? Well, all you need to do now is plug it in, okay? Plug in the two cases. So we have our first case of the outside radius being 4 millimeters and the inside radius being 3, as always, right? Always. And then the outside radius for this is 7, right? And essentially you'll plug it in and find Q. Find Q. And before you even do that, think about it. If we have the same temperature difference, but we have a 1 millimeter, right? Versus a 4 millimeter distance, right? We can assume, right? And the temperature difference is the same, right? We can assume that the Q is going to be lower than scenario 1, right? We have the same heat difference, the temperature difference, over a much longer path in scenario number 2. So if you're getting this one to be higher than this one, that means something's wrong. Maybe something's being plugged in incorrectly, maybe something's split. So try to understand why your answer is what it is. All right? Great. Well, let's keep going. So part B is asking you to now plot Q and plot the mass of the tube. So 2 different plots, right? These are 2 different things, 2 different plots as a function of wall thickness. Wall thickness. And then you're also given a range of wall thickness. Well, let's think about that. So we have essentially 2 plots. We need to make 2 plots, okay? This is not a plot, okay? This is for your reference. Okay, so plot 1, plot 2, your X and Y direction, right? Whatever you're plotting. Well, we know Q, right? We just determined Q is 0.4 watts over natural log R0 or R outside and over R inside. And for this second plot, it's asking for the mass of the tube. Well, we don't know that yet. Okay, well, let's first look at plot number 1. There's no thickness in this expression, right? But what did we say was changing? Well, it's that outside radius. That outside radius is changing directly proportionally with thickness, right? So this changes. And we can use it as an analogous variable for thickness. So we can just say R0, okay? That means, well, our range of thickness was given, right? T is for thickness, not time, thickness. What does that mean? Well, we know the internal radius, inside radius, is 3 millimeters. That means simply we're going to plot with this. That's how you can still use your original expression, or if you want to, you can change that R0 to like 3 plus T or some variable thickness. That's okay too. But I'm just showing you, you can also just change the range and make this problem easier to solve. Okay, now what about the mass of the tube? What's the mass of the tube? Well, let's think about it. So the mass of the tube, we have our tube, right? I'm gonna draw it out a bit, just faster. So we have our tube right here, right, with some thickness, that's the mass. The thickness of the silicon is the mass. So right over here, this is all the mass we're trying to find. What is this, right? What is this? Well, as you recall, right, if we have R out and R in, well, what's the area? What's the area of this? What's the area? Remember, I know a lot of you all did this last quarter. We talked about it. That is not true. That is not true. Absolutely not true. Right? We talked about this. So let's make sure we don't mess this up. It's going to be pi r squared, right? So pi r squared minus r inside squared. Do we recall this? Recall. Right? This is what we said was the area in between two circles, right? Great. So that means the volume is going to be area times length, right? And what did we say our length was? We said it was 10 centimeters, right? So that's going to be pi r outside squared minus r inside squared times length. Then what is the mass? Well, we have volume. What do we need to find mass from volume? Well, we need density. And luckily, we are given density earlier in this question. All the way at the top, we have rho equals 1.1 grams over centimeters cubed. So we do have density, we do have volume. So what that looks like is going to be pi, sorry, we'll have the rho up front. Rho pi r0 squared minus r I squared times length. And there it is. That's the mass of the tube. And what you're going to do is you're going to plug it in. You can make some constants like we did previously. That's going to make things easier. And that equals rho pi r outside squared minus r inside squared times L. And you can plot these two either by hand or MATLAB, whichever one you prefer. And that is the answer for part B. So good luck on that. And let's move on to the next question. All right, so let's get started with question 2. I'm just talking about insulation of two walls. So we are insulating two different rooms at two different temperatures. And the word wall refers to the entire heat conducting surface of a room. So just as we set up this question, it doesn't really matter the shape of the room or one wall or whatever the question is saying. Essentially, the wall is just the heat conducting surface. It's the cross-sectional area. All right. So let's not get too confused by this part. It's just saying the spaces right over here that we're given, it just refers to what area is heat conducting. It could be anything, right? So let's keep going. We have room 1 as 30 degrees Celsius inside, and room 2 is 15 degrees Celsius inside. So right away, I'm going to start keeping track of this information below. We'll maybe just draw a line right here and say this is room 1, and this is room 2. All right, so we have also, looks like the wall area of room 1 is 6 meters squared, and the wall area of room 2 is 12 meters squared. So we can just draw an arbitrary room, right? Doesn't have to even be a square, we don't know. It's just somewhere like heat conducting, 6 meters squared. And I'm not saying this is the area, okay? Actually, that's going to be confusing. Let's say surface area is 6 meters squared. So surface area, just heat conducting area, okay? And our second is going to be 12. So we can expect the room to be bigger, at least. Okay. And we know the temperature inside room 1 is 30 degrees Celsius and inside room 2 is 15 degrees Celsius. And the outdoor temperature for both rooms is 0 degrees Celsius. So we know right away heat's moving from in to out, right? And now here's where it gets a little tricky. 1 meter square of wall without insulation has a thermal resistance R. So, and it looks like there's a typo, just repeated twice. And then 1 layer of insulation has thermal resistance 2R. And 2, it has 3R. So that's pretty critical. So we know that no insulation is R, 1 layer is 2R, 2 layers is 3R, so it's a +1 essentially, right? And here's also another key part. We can combine thermal resistances like parallel resistors. So 5 meters squared has 1/5 the thermal resistance and 1 meter squared. So what does that mean? So if we have, let's say, we have 1 layer. Actually, let's start with the example they gave us. So 5 meter square wall, right? That means the resistance is going to be 1 over R plus 1 over R plus 1 over R plus 1 over R plus 1 over R, right? That's 1 over 5R, okay? Does that make sense how we're adding parallel resistors, right? So this is where we draw this analogy as well. Okay, so I hope that makes sense. We're going to keep going and we can talk about how much insulation we have in a moment. I want to kind of break this down and let's look at this a little more. Question A, part A, is asking how should you distribute the insulation in order to minimize the combined heat loss between the two rooms, or sorry, from the 2 rooms, right? So the combined heat loss, big Q, right? So let's think. We have Tn, right? The inside temperature, and T out, which is obviously lower. And we have heat moving from inside to outside, right? We are trying to minimize big Q, right? We know from Fourier's law, we have Q dot equals big Q over cross-sectional area, right? And we also have Q equals negative K dt over dx, right? Well, let's think about it. When we're changing the resistance, when we're adding insulation, what are we doing? We're changing K. We're changing that, right? Essentially, we're changing the conductivity or the thermal conductivity of this entire room, of the surface, right? It's changing. Right? Is the temperature changing? The temperature difference? No, right? Is the cross-sectional area changing? No. It's the amount of insulation that we're changing and we're trying to minimize. We're minimizing Q, right? So if we're minimizing Q, we want to set them equal, right? Looks like we also have the temperature difference, we have the cross-sectional area. So we want to set these two together, similar to what we did earlier. So Q over cross-sectional area is negative K dt dx, right? And essentially, we aren't really given the thickness of these insulating layers, right? So for now, we just know the change in temperature. We can take this as well as the negative to know this is representing the change in temperature and a negative in front of it, right? We also have that negative from here. So let's say we solve for Q. Solve for Q, and that means we have negative K times the cross-sectional area times our change in temperature, right? Since we're not sure about that thickness. Well, so what's really changing here? K, right? And we also know K is going to be 1 over the total. We know that when we add up parallel resistors, it's this. Our total equals 1 over R plus 1 over R, etc., right? Whatever we add up, it's 1 over R total. This is our K, right? So that means we have, therefore, an expression Q dot is equal to the negative cross-sectional area over R, right? R total or R for room 1, and then this can be Q1, right? Times the change in temperature. And now we have an equation. We have an equation. Yay, we have an equation. Now we can minimize Q. We need to minimize Q as much as possible. Now going back to the question, we have 24 meters squared of insulation, and it can be divided in 4 equal pieces. So that's enough to cover all of wall 1 or half of wall 2. And essentially what it's saying is we can stack the insulation as well, right? Remember, we're not covering like 6 different walls here. That's not what the question is saying. It's saying the wall of which heat can flow is 6 or 12, right? So let me write that out. So we have 24 meters squared insulation, right? And we have 4 pieces. 4 pieces of 6 meters squared insulation. That means with 1 piece, we can either 1, cover all of room 1, right, once, or we can cover half of room 2. All right, because half of room 2, this is 12, right? And this is 6. That's what it's saying. So let's start by actually seeing the parameters of this question, all right? I'm going to draw this again. Actually, I'm not going to draw it. I'm going to write out what we need. We have room 1 and room 2, right? We have room 1 and room 2. That means we know first, the change in temperature is 30 to 0, right? So that's 30 Kelvin. And we have the change in temperature, again, is 15 Kelvin, right? And that's negative, keep in mind. And that's important because we also have a negative up here, right? So that means these negatives will ultimately cancel out later. Let's keep going. The cross-sectional area we know of heat flow is 6 meters squared, right? It doesn't matter how many walls. It's just the cross-sectional area is 6 meters squared of flow, okay? And then 12 meters squared here. And what's the resistance? Well, that's where we play around and see what is the best option. So that means if we are going to write out our expression Q, our overall Q, right? Q total combined is going to be from room 1 and room 2. So if we plug in using this equation we determined above, AC over R, the negative AC over R times the delta T, that means we have, right? I'm going to cancel the negative with the 30, negative 30K. So we'll go with that first. We have our cross-sectional area over our unknown R, right? Our unknown R, and we have times 30K, right? Kelvin, 30 Kelvin, right? And then we also have plus 12 meters squared over unknown R, right? Times 15K Kelvin. And essentially what we can do, we know we're trying to find how many layers of insulation. We're going to simplify this equation as much as we can. So we're not going to do redundant calculations or solve Q for every single calculation. If we solve that, like I did last year, it's going to take a long time, let me tell you. This is a much faster way, okay? So instead, what if we said, well, we know that no layers is R, one layer is 2R, right? 2 is 3R, 4, blah, 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 right? So that means it's n plus 1, right? N plus 1. That's the pattern, n plus 1. So that means we can say n plus 1 here, R. So if we have 0 layers, n is number of layers, we have R, right? And that's correct. That is correct. And what I'm going to do, I'm going to also denote this as N1 to keep it separate from this, N2. N2 plus 1. N2 plus 1, right, is in room 1 and room 2, right? Room 1 and room 2. Great. Let's keep going. So N is the number of layers, N1 is room 1, N2 is room 2. These correlate like this, right? But here's the problem, right? The thing is, room 2 is 12, right? So that means potentially I could, let's say, I'm just going to draw an arbitrary wall right here, and this is 12 meters squared. What if I want to apply 3 layers here and 0 layers of here, right? That's going to be different than if I apply 2 and 1, right? Is that right? Yeah, that's right. 2 and 1, right? 2 and 1. Why? Because, well, this is 1 over 4R, right? 4 because it's 3 plus 1 plus 1 over R. And that's not equal. That's not equal to 1 over 3R plus 1 over 2R, right? It's not the same. So we need to keep that separate and denote that. And I'll show you the actual math of why, okay? In a second. So just follow along with me. Another thing is, well, if we still go about this and try to find the ends, we're going to have to calculate this completely out. So what's a good way to simplify this? Well, the best way is to simplify the 12 meters squared and make it as if there are 2 different walls of the same room. The temperature is the same, right? And this would just be divided by 2. So what does that mean? We're going to just break this apart into 2. So that means it would be 6 meters squared, right? Over N2 plus 1, R, right? Unknown R, 15K, plus another room or another wall. We just divided the walls, right? And this is N3 plus 1 to denote that we can place it in a different position, okay? I know this might be confusing, but we're essentially breaking the wall into 2 pieces, which allows us now, right? And then we're going to carry this over from here, right? I'm using R. I'm using a black to denote that it's carried over, right? That means if we see we have 6, 6, 6, right? And then we have 30K, 15K, 15K. And then we also have R, R, R. So that means we can pull it out and just keep the ends by themselves, right? That's the key part. So that means we can do Q total equals, let's pull out the 6. Let's also pull out all of the R's, right? And then let's also take out the 15K, 15K. So that means this is pulled out, meaning we have 2, because this is 30K, right? So that's 2 over N1 plus 1 plus 1 over N2 plus 1 plus 1 over N3 plus 1, right? This is a simplification that allows us, all we have to do is calculate this. We only need to calculate this. And how nice is that? That means we don't have to keep calculating Q total for every single possibility like I did. And what's better is you can either do this by hand or do an Excel sheet, whichever you prefer. But this makes it a lot easier to do by hand. All right, so let's think about it. We have 4 sheets, right? We just talked about it. We have 4 sheets of insulating material, and they can go in either N1, N2, or N3, right? So let's think about it. Let's actually draw a table now. So I'm going to draw a table. Oh, sorry, I don't want to use red. So there's a reason I'm using a thick line. That's because of this. So I'm going to draw a table. And of course you can do this on Excel or a faster method. But just to show on this video, I'm going to draw it out like this. So we have a table right here, which allows us to start now writing our possible combinations. N1, we have N2, and we have N3, right? And then we also now have our expression that we need to calculate. We have 2 over N plus 1, N1 plus 1, plus 1 over N2 plus 1, and then plus 1 over N3 plus 1. And then we can actually calculate it out total, right? So I'm going to show just a couple examples, right? And I'm not going to do all these calculations, so that's up to you to do. So first, we could put all of our 4 layers on N1, which is the first room, right? It's the first room. First room with the 30K, right? We put all the insulating layers and leave room 2 empty. That's the first possibility, right? That means it would be 2 over 5, not 4, 2 over 5. And that's not it. We still have 1 over 0 plus 1, which is 1, and then 1 over 1, right? So this has this value of what? 2.4, right? 2.4. And what we're going to do is we're going to go down the line. Well, 3, 1, 0, right? I'm going to move one of these layers to one side. And this is the same as this, right? It's the same. They're equivalent. So you don't need to do that. Right? So you're going to do this out and see what is this value? What is this? What is this, right? And we're essentially trying to get the lowest total possible, because the lower this value is, right? This entire expression, the lower it is, the lower Q total will be, and we minimize that heat flow, right? That's our goal. So let's keep going. Now we even decrease it to 2 layers in that first room. And this is where we need to think, right? So we could either put 2 of our layers on half of the room, right? Half of the wall, and leave the other wall empty, right? Or we could do an even split and cover both sides or both halves of the wall in room 2. This is both room 2. Remember, this is room 2. They're both room 2. And that will actually give us a different answer. Why? Because let's think about it. Well, we have 2 over 3 plus 1 over 3 plus 1 over 1. And we have 2 over 3 plus 1 over 2 plus 1 over 2. Last time I checked, these answers are different, right? They are different. That means because we're adding resistors in parallel, right? They are different. So you're going to keep going all the way down the line, and I'm just going to also work out the 0 for you. For example, 0, if you do zeros, some zeros over here, and then say like 4, 3, and then another option can be 2, 0, 1, and 2, right? Essentially, we have 0 layers. This is not ideal. Why? Because we have 2 over 0, or sorry, 2 over 1, right? It's plus 1. That means you already start with the 2, okay? Plus whatever we have, right? Plus, or whatever. So this is going to be a much bigger number. So you can still calculate it out and try it out, but just expect a really big number, right? Bigger numbers there. For example, I'll just do this first one. We have 2 over 1, that's already 2. And then we also have 1 over 5 plus 1 over 1. That's already 3.2. That's so much bigger than the 2.4. So keep that in mind, okay? And that especially, you can also think about it. Well, the room with the higher temperature difference, we'll want to make sure that that room is insulated, or that room is going to lose a lot of heat, right? You can also think about it in that way. Great. Let's move on to part B. So if you estimate that the total heat loss through uninsulated wall 1 is 600 watts, what is the thermal resistance of all of wall 1? Well, the thermal resistance, and there's a fancy way to denote the R, but I'm not too sure about that. But anyways, the thermal resistance, not resistance, right? Thermal resistance is defined as the change in temperature over Q, okay? Change in temperature over Q. So you can just plug in for Q because we have the total heat loss, right? And then you also know the temperature difference. So therefore, you can calculate the thermal resistance. So that's straightforward, easy. And then part C is if the wall 1 is 2 inches thick, so we have a thickness now, right? What is the thermal conductivity of the material? So what is K, right? What is K, right? The actual value of K. Well, we also know the thermal resistance is equal to length of which heat flows, right? Length, also known as thickness, right? Length or thickness. And we know it's over K times cross-sectional area. Well, great. We know length now, right? We know our thickness. And we also know our cross-sectional area. And we also know now RT from here, right? So we can just rearrange for K, right? K equals L over thermal resistance times cross-sectional area. And one thing to note is we are given length in inches. We need to convert it, okay? Make sure you convert that to meters. Okay, so that's the end of question 2. Let's jump right into the final question for question number 3. All right, let's get started with the final question of this homework. So this question is about heat loss through the skin. And we're given information about the specific heat capacity and the humidity. So please read through that. And we're given several assumptions. So I'm not actually going to read through this This can be done on your own. And we're actually going to keep looking. We're also given some hints right over here. We'll take a look at that in a second. So we are given the human body at rest generates 100 watts of heat. What's a watt? Well, a watt is a joule per second, right? So 100 watts of heat. So if this heat did not leave the body, we would warm up to the point where body functions cease and we die. So that means, right, we don't have any accumulation of heat, right? If we accumulate it even a little bit over time, we just heat up forever, right? So we don't have heat accumulation. That's an assumption. And it's asking at what average rate does heat escape through the entirety of our skin? Only the skin. So let's take a step back and let's look at the earlier parts of this question. So we're told we can ignore heat transfer from urination, food consumption, and water intake. And that means what's the only thing left? Well, we have our skin, number one, skin. And most importantly, our lungs, right? If you really go from like head to toe, if you think about it, we only have, with these assumptions, we only have our skin and we have the air that we breathe. That's the only other way that heat is going in and out, right? And we're also told, we're given some other hints. We need the heat of vaporization. And we also need the air consumption rate and the skin surface area. And yeah, we'll be glad to help you for sure. So these you can find online, okay? So let's actually think about this. So we have our human body. I'm gonna draw person. Oh, one leg is a little shorter, it's okay. So we have a human person right here, right? And we have 100 watts being generated, right? Joules per second. And we also know what. Let's take a look at these assumptions. We're giving the ambient air is at 82 degrees Fahrenheit and 40% relative humidity. We're given absolute humidity at 28, 37, and we're given density of air. And we're like, well, what do we need all this for? Well, I hope the number 37, I know that we all talk about body temperature in Fahrenheit, but hope the 37 is a little familiar because that is our human body temperature in Celsius, 37 degrees Celsius, okay? And essentially the 28 degrees Celsius, right? There's the 82 degrees Fahrenheit, which is the hint, right? So 82 degrees Fahrenheit, if you do the calculations, it's very similar. So it's actually equal to 27.78 degrees Celsius. So that's essentially 28, right? That's essentially 28 degrees Celsius. Great. So we're given the absolute humidity inside our body and outside in the air. We know that. We're given the relative humidity in the air. And we're also given the density of air at our body temperature. So we have heat escape through the skin, right? But we also have heat escape through the lungs, right? And if we really think about it, our lungs, there are two things, right? Let's think about it. We're asked to find heat of vaporization, right? And what's also discussed, the specific heat capacity. What are those for? If we go back to our old chemistry classes, right, where we were learning about thermochemistry or thermodynamics, right? We know heat capacity is used for heating, right? Heating. So in our lungs, right, air is being heated, right? That's what the specific heat capacity. What else? I'm actually going to, yeah, this is number one. And number two, the heat of vaporization means that there's evaporation going on. Evaporation, right? HVAP. Hopefully this rings a bell. There's evaporation going on, okay? We're going to talk about this in 1 second. Let's actually jump right back to the question, okay? So that's an introduction to this question. So at what average rate Q does heat escape through the entirety of our skin, right? Well, we know there's zero accumulation, right? And we know that there's generation, right? The 100 watts. I'm going to leave it as Gen for now. And then we have heat leaving through our lungs, as we just mentioned, and our skin. That means we can find the heat escape from our skin by finding, right, Q gen minus Q lungs. We already know Q gen, so all we need is Q lungs. What is this? This is what we're trying to find. So we need to always set this problem up well, right? Figure out what we're looking for. Well, we just talked about the two components that go into the lungs, right? Two components. We said one was vaporization, right? Evaporation, right? And evaporation of what? Evaporation of what? Evaporation of water vapor, right? We're going to talk about it in 1 second. Of water, right? Two, heating of air. We're heating the air that we're breathing, okay? So hopefully we understand this, right? So we know this. Let's start with the evaporation of water. Let's talk about this. So let's recall on a cold day, right? On a cold day, we see a cloud of air when we breathe, right? We see vapor. Why? Because our gas is becoming a liquid, okay? And it's becoming a liquid because the colder the air is, there's a low energy. So we know gas, you know, all those gas molecules have high energy. They're moving around in a frenzy. And since the air has such a low energy, it becomes a liquid, right? And it becomes water vapor, right? We know this condensation, right? Actually, I don't want to draw an arrow. That's confusing. Condensation, right? But on a normal day, right? On a hot normal day, as the gas leaves, most, if not all, remains a gas. It still remains as a gas, right? And the reason is because in a warmer environment, in warmer air, right, there's still high energy, right? It's not too different from our internal body. It is different, but still not as different as cold weather, right? So it still remains a gas. So what about as the air enters our lungs? Sorry. So these are our lungs, right? So as air enters our lungs, right? We have some water molecules, water, being evaporated. It's turned into gas. And why is that? The reason for that is because the humidity at our body temperature is higher, which means it can hold more water in its gaseous form, okay? That's what it means. So that means as the air enters, right, we know that the humidity, the absolute humidity for saturated air, right, outside, it's 0.028 kilograms per meters cubed, right? That's from the prompt. And then inside the lungs, it's 0.045 kilograms over meters cubed. Okay. So that means we have water being turned from liquid to gas as we breathe in air. Okay. As we breathe in air. That's one component of the lungs. Okay. That's the first component. It's evaporation of water into gaseous form, right? If we had water build up in our lungs, that would be very, very detrimental to us, right? So we have evaporation of water as we breathe in. So the real question is, how much water? How much water? Well, that's where we have the percentage of relative humidity. So that's the percentage of the amount of the absolute humidity, right? So it gives us a percentage of the absolute humidity. So we know inside the human body, what do we think the relative humidity is? It's 100%. It's 100%. 100%. And outside, it's 40% as given in the prompt, okay? So that means how much mass? That's our question. How much mass of water, right? How much is being evaporated, right? We need that. We find that out by, you recall, we multiply the fraction, right, of the percentage. We multiply the percentage as a fraction of the absolute humidity. So what does that look like? We have our outside 100% or inside 100%, 0.045 kilograms per meters cubed minus 40%, 0.4 times 0.028 kilograms. So if you notice, this is not in grams though, right? We have a meters cubed. And why is that? It's because this is mass. Oh, right, it's the rate. And we can determine, right? We can get kilograms by knowing how much per second. Let's recall that the question also asked us for our air consumption rate. The air consumption rate. The air consumption rate will give us what? It will give us liters per minute, right? Okay, liters per minute, okay? It gives us liters per minute. So that means, what is liters? Well, liters, meters cubed. And can we keep this in minutes? No, we need it in seconds. Why? Because watts is equal to joules per second. And we're trying to find Q. Do we see the connection here? So we're trying to find Q of this process. And then we're going to find Q of the other process. And we're going to add them together. And that composes of the Q for the lungs, okay? So let's keep going. So you're going to find the air consumption rate from Google, you can test it out, whichever one you give, as long as it's reasonable, will be fine. And now we need to find Q evaporation, right, is equal to, we have our m dot, right, that we find by multiplying this. So this is going to be this times, right, times the air consumption rate in liters per minute. And then you can find the conversions to get it into meters cubed over seconds, okay? So actually, I'm going to write that out again. So we're going to have this is going to be what we just wrote above, right? The 1 times, so we have 1 times 0.045 kilograms meters cubed minus 0.4 times, sorry, Okay, that's confusing. Okay. Times 0.028 kilograms per meters cubed times air consumption rate. And that's going to be in meters cubed over seconds. Okay. Great. So now we have that. We need to multiply it by the other value that we were asked for, right? And HVAP, you need to find this at what temperature? At 37, at body temperature, okay? At body temperature. And if you do some, I know there are lots of resources. A good one I saw online was the Engineering Toolbox website. I think it's like engineeringtoolbox.com or something like that. You can just plug in the temperature and find it. And the great thing is it gives you the values in kilojoules per kilograms, right? I mean, you could do kilojoules per moles, right? But that would mean you have to do an additional calculation to convert from mole to gram, right? Why not make it more simple, right? So use this relation if you can, okay? So therefore, that will give you the Q for the evaporation. This is our first, right? Evaporation. Recall, right? Recall that we have two components. We just did evaporation of water, done, right? And now we have two. We have the heating of air. It's not just water evaporation that occurs. We also have heating of air, right? Heating of air. And what is the heating of air? I wonder if we all remember this. It's a beautiful equation. I'm just going to use heating to denote it. MC delta T, MC delta T. Wow, it's been a while, right? It's been a while for me too. MC delta T, and we all know this. And the question is, how do we get M? What's the mass of air? Well, as we said, mass is rho times volume, right? And remember, the dot represents the rate. So that means we have our volume rate, which is what? We just talked about it. It's the air consumption rate, right? And then we also have density of air. And we are given this earlier. We have density of air, 1.15 kilograms over meters cubed. Right? So with that, we can first, we have M. We also know CP, we're given it earlier in the prompt. And we also know delta T, right? Delta T is 37 degrees Celsius minus 28, right? So we have everything we need to find Q of the heating of air in the lungs, right? We should have everything we need. That means, therefore, finally, the overall heat loss from the lungs is a combination of Q from the evaporation plus Q of the heating of air, right? And therefore, right, therefore, as we mentioned earlier, the skin is going to be the generation, 100 watts, right? Minus Q lungs, okay? Q lungs. And that will give you your final answer, okay? You should have something like this in the terms of watts, units watts, okay? Great. And, oh, somehow my question got moved down. Okay, that's okay. What is the average heat flux over the surface of the skin? Well, remember, Fourier's, right? Q cross-sectional area, right? And this is Q skin. And we know that the surface area of the skin ranges from, I believe it's 1.5 to 2 meters squared. So whatever, you can estimate yours also online, I believe. So that'll be a little fun. You can plug in different numbers in the range, and that will give you Q. And you'll have an answer for that. Okay. So that is the walkthrough for question 3 as well as for homework 1. Thank you all for watching. If you have any questions, please drop by my office hours tonight. And if you missed the office hours, please just send me an email. I'll do my best to get to those emails and help you out as much as I can. Remember, I can't help you if I don't know you need help, okay? So please make sure when you to communicate when you need help. Again, thanks for watching. Hope you all have a great rest of your day.